Welcome to this presentation from the series Electronics, the story of one human lifetime, presented by David Beams and Gary James. I am Gary James, retired graphic designer, and worked with David in producing this piece. In this presentation, you will see some examples of historic vacuum tubes. We hope that the progress in vacuum tube technology will be apparent in the following images, and that you gain an appreciation for the talent, energy, and ingenuity that went into vacuum tubes during their decades of dominance in the field of electronics. The next 3 slides contain definitions of some terms that will be used in this presentation. Cathode, plate, grid, diode, and triode. Tetrode, pentode, beam tetrode, thermionic emission, photoemission, secondary emission, directly heated cathode, indirectly heated cathode. The next few slides will show examples of early vacuum tubes. First, we have the UY227 triodes, which were introduced in 1927. They bear a strong external resemblance to incandescent lamps of that era. The base is bakelite, the earliest synthetic plastic material, and there are 5 pins, 1 each for plate, grid, and cathode, and 2 for the heater, suitable for audio frequency applications. Cunningham CY327, another variant of the same basic triode. Here are some examples of early triodes and tetrodes. These are Philco 27 triodes, yet another manufacturer of this basic triode. These are RCA Radiotron 35 and 235 tetrodes. An indirectly heated tetrode would require 6 connections, 1 each for plate, cathode, control grid, and screen grid, and 2 for the heater, which the 5-pin base would not accommodate. The 6th connection was made through a metal cap on top of the tube. The screen grid provided electrostatic isolation between the plate and control grid and greatly increased the maximum frequency at which the tube could amplify. The RCA 35 was introduced in 1931 for radio frequency applications. Notice the silver coating inside the tube. This was a thin film of a chemically reactive metal whose purpose was to react with and bind any stray gas molecules that remained in the envelope when it was sealed. The process of using a reactive film to capture stray gas molecules was called gettering. A close-up view of the RCA 235. The cap is connected to the control grid. The plate is a mesh cylinder. The control grid is readily visible. The screen grid is just visible. Octotubes with 8 pins and a bakelite base were introduced in the early 1930s. The 8 pins were arranged symmetrically, but a central locating key allowed the tube to be inserted into its socket in only one way. The first octotube we will look at is a 35Z5 rectifier diode used in power supply circuits. Beginning in the 1930s, many tubes were given designations that consisted of a number, 1 or 2 letters, and a number. The leading number, 35 in this case, designated the rated operating voltage required to heat the cathode. In this case, the heater required 35 volts at 150 milliamps. Note the base. Note that some of the 8 pins are missing. Unconnected pins were sometimes omitted. Note the locating key. These tubes are from the late 1930s. The 6SC7 is an example of enclosing more than one active tube within the same envelope. Note that these tubes use metal shells in place of glass envelopes. Electrical engineers use schematic diagrams to represent the circuits they design. Here we will show schematic symbols of the 6SC7 twin triode and the 12SK7 pentode. The schematic symbol of the 6SC7 is showing the plates, grids, cathode, and heater. Note that the 2 triodes of the 6SC7 share a common cathode. There are some electronic applications where having 2 electrically matched tubes sharing a common cathode would be advantageous. Schematic symbol of the 12SK7 pentode is showing the plate, control grid, cathode, screen grid, heater, and the suppressor grid. The suppressor grid was introduced as an improvement to the tetrode to solve the problem of secondary emission electrons from the plate flowing back to the screen grid. The suppressor grid was operated at ground, 0 volts. In some pentodes, the suppressor was internally connected to the cathode. This slide shows examples of beam tetrodes. Here we have the 6V6 beam tetrode and the 50L6 beam tetrode. The secondary emission phenomenon of the tetrode was suppressed with 2 electrodes that form the electron flow from cathode to plate into 2 beams 180 degrees apart. These electrodes were connected internally to the cathode. The beam tetrode was developed as an alternative to the pentode, in part to avoid patent issues. Beam tetrodes were very common as the output stages of audio amplifiers used in entertainment electronics, where they were known as beam power tubes. schematic symbols of the beam tetrode. This is the basic symbol showing the plate, control grid, cathode, screen grid, heater, beam forming electrodes. Beam tetrodes were often shown on schematics as pentodes. A variant of the octal tube was the Loctal vacuum tube. The Loctal vacuum tube had an 8-pin base in which the pins were embedded directly in the glass envelope. This required developing an alloy of nickel, cobalt, and iron with small amounts of carbon, silicon, and manganese, known as covar. The thermal coefficient of expansion of covar closely matched that of glass, so that the glass to metal seal was durable through multiple cycles of heating and cooling. Note the central locating key that ensured the tube could only be installed in its socket one way. This is a 7A6 twin diode. Schematic showing the plates, cathodes, and heater. Miniature vacuum tubes were introduced in the early 1940s with 7 or 9 pins directly embedded into the glass envelope. The tubes shown here are 12 AT7 twin triodes introduced in 1947. They were popular in audio applications. These other types of twin triodes were quite similar. Schematic, including the plates, the grids, the cathodes, and the heater. The 12 AT7 heater had a center tap so that its 2 sections could be operated in series from 12 volts or in parallel from 6 volts. The 12 AT7 on the right has lost its vacuum from a failed seal or a small crack in the glass. The Gettering film has completely oxidized and has turned transparent. Miniature tubes for power amplification applications. Here we have the 50C5 beam power tube and the 6CL6 power pentode. These tubes were very widely used in the output stages of many audio systems. This is the 50C5 basing diagram. Note that it is drawn with a standard pentode as a standard pentode, even though it is a beam power tube. The 6CL6 basing diagram. Note the power required to heat the cathodes of these tubes. This gives some idea how inefficient tubes were. In many electronic systems, the largest part of the energy consumed by the system went into heating the tubes. Other examples of miniature tubes. Very compact miniature tubes for VHF and UHF applications. These tubes are approximately 2.5 centimeters in height. The 2AF4 was introduced circa 1940. An example of a multifunction vacuum tube. This is a 12AB6 combining a triode and 2 diodes sharing a common cathode. Very commonly as detector, automatic volume control rectifier, first audio amplifier of mini radio receivers. also available with different heater voltages. This is the basing diagram of the 12AB6. Note that all three tubes share a common cathode. This slide shows some special purpose tubes. An acorn tube, named for its shape, very small dimensions for VHF and UHF operation. A hearing aid tube with leads instead of pins. Tubes for battery-powered applications had to be customized for low plate voltages and usually used directly heated cathodes. 8 leads would be required for a directly heated twin triode. OA2 mercury vapor voltage regulator tube. Note the leading number 0 of the type. The mercury vapor voltage regulator did not use a hot cathode and therefore had no heater voltage. Its conduction mechanism used ionized mercury vapor. The operating voltage remained almost constant over a wide range of currents, allowing its use as a voltage regulator. Schematic diagram of a shunt regulator circuit using a mercury vapor voltage regulator. The OA2 provided a regulated voltage of 150 volts, while the OB2 was a 108 volt regulator. This slide shows tubes for high power operation, often for radio transmitters. These are the 3 types we will look at. 572B triode, a pair of 572B triodes could produce close to a kilowatt of output power in a radio transmitter. Note that the cap of the tube is connected to the plate. 807 beam power tube. Very common in medium power radio transmitters, especially in amateur radio use. Also used for high power audio amplifier applications. 6146A beam power tube. Also frequently used in medium power radio transmitters. Later developments in vacuum tube technology. An example of a tube in a 12-pin compactron format. This is a 6LU8, which included a triode and a beam power tube in one envelope. The 6LU8 required almost 9.5 watts to heat its cathodes. The 6LU8 was intended for use in color TV applications. The pinnacle of development in the vacuum tube was the RCA New Vista series, introduced circa 1960. This is a 6CW4 triode. The compact size of the New Vista made it suitable for VHF and UHF applications. For comparison, here's a side-by-side comparison of the 572B and the 6CW4. Note their relative sizes. The 6CW4 is less than 1 inch tall when mounted in its socket. Compare with the dimensions of the 572B. These tubes are meant for very high voltage applications. These are both diodes, and the use of a cap is not required because of a lack of pins. The cap is meant to give the greatest possible separation between the plate and cathode terminals, since these tubes were meant to operate at up to 25 kilovolts. These tubes were often operated in shielded cages to stop any soft X-rays which they could produce. The octal tube on the left has been identified. The markings of the miniature base tube has been worn off. Let's look at some more exotic vacuum tube examples. 4-1000 transmitting tetrode, directly heated cathode, 1000 watts continuous plate dissipation, required forced air cooling, used in commercial transmitters, plate voltages 3 to 5 kilovolts. Rotating anode X-ray tube, operates at extremely high voltage on the order of 100 kilovolts. Rotating anode prevents damaging power dissipation from the beam falling only on one spot. Cavity magnetron, developed in the UK, brought to the US in September 1940 as part of the TIZARD scientific mission, allowed compact microwave radar suitable for aircraft use, which played a key role in defeating the U-boats in the Atlantic during the Second World War, still widely used in microwave ovens. Klystron UHF amplifier tube from the 1950s, used in television transmitters. Let's look at optical developments with tube technology. Light sensing tubes use cold photocathodes, materials that emitted electrons when they absorbed light photons. This was known as the photoelectric effect. A special phototube, called a photomultiplier tube, also used secondary emission to achieve great sensitivity. The photomultiplier tube included a photocathode, an anode, and intermediate electrodes called dinodes. Dinodes were operated at progressively higher voltages. The anode is held at ground potential, usually by a circuit called a charge amplifier. The photocathode is held at a negative potential, minus 500 volts or so. The photocathode emits electrons when it absorbs photons of light. The photoelectrons are accelerated towards the first dynode, where they arrive with sufficient kinetic energy to dislodge additional electrons through secondary emission. The electrons from the first dynode are accelerated towards the second dynode, where they again cause secondary emission. The electrons from the second dynode are accelerated towards the third dynode, where they again cause secondary emission. At each successive dynode, the electron pulse becomes greater until the pulse is collected at the anode. The charge amplifier produces a voltage pulse from the pulse of electrons. Another example of light sensing vacuum tube technology. This is an RCA image orthicon television pickup tube from the mid-1960s. This technology has been superseded by the solid-state charge-coupled device image sensor. Let's look at technologies made possible by vacuum tubes. First, radio. The photo is of Edwin Armstrong, inventor of the superheterodyne radio receiver, still used in almost every radio and television receiver on the planet, and FM radio. He was a fascinating individual whose life ended tragically. An All-American 5 radio receiver of the 1940s, so named for its use of 5 tubes. Another technology made possible by vacuum tubes, radar. The photo shows a tower and antenna of the British chain home radar system that was crucial to British success against the Luftwaffe in the Battle of Britain. Sir Robert Watson Watt, Scottish radar pioneer and architect of chain home. a mobile microwave radar fielded by U.S. forces in the Second World War. Another advanced technology first implemented with vacuum tubes, television. Philo T. Farnsworth, inventor of raster scanning image dissection. Farnsworth is the only engineer represented in Statuary Hall. Vladimir Zavorskin, Russian-American television pioneer. Zavorskin developed the cathode ray tube, CRT, and the iconoscope, TV pickup tube. A copy of Zavorskin's patent for an all-electronic television system. And yet another advanced technology using vacuum tubes. Digital computers. Origin of the term bug comes from an incident in which a malfunction of a vacuum tube computer was traced to a moth caught in the machine. But a revolution was coming. From the UY227 to the 6CW4 was a span of just over 40 years, about the duration of an engineer's career. But the solid-state revolution began in the late 1940s with the invention of the transistor. By the close of the 1960s, the reign of the vacuum tube was clearly coming to an end. RCA closed its tube manufacturing plant in New Jersey in 1976. At the time of its closure, it was the largest in the world. We hope you have been impressed by the incredible developments from the early days of electronics and have come to appreciate the ingenuity of those who made them happen.